All right, so let's wrap up today with an example. So here is some code. I believe this is actually from your textbook. So we'll have some initial values for the stack pointer and the instruction pointer, or the program counter. And here is the code. So here you can see the binary representation in hexadecimal. Over here, this is the compiled x86-64 code. Here are the assembly language representation of these instructions. So here is a slightly different formulation of it. So here's the code over here. I've gotten rid of the binary because it's not important to tracing through the code. Here are some registers that will be useful. So we have RIP, RSP, RDI, and RAX. We don't know what the values of RDI and RAX are right now, so I put question marks there. And then there are some regions in memory, some slots in memory that are going to be useful. These are ones that happen to be just past the top of the stack, and over the course of this example will become part of the stack, at least temporarily. But we don't know what is in memory at those locations, so I've just filled them in with question marks. Okay, so at this point, I would recommend pausing the video and seeing if you can figure out what's going to happen, at least for the next couple of instructions. And I would encourage you to continue doing that throughout this video. So even if you don't work out the entire thing right now, watch a couple of instructions and then pause it again, make some guesses, and see if you can get to the point where you're comfortable understanding everything that's going on here. Okay, so right now the program counter is at, and I'm not going to read off all these huge addresses, so I'm just going to kind of refer to things using the last 3 hexadecimal digits. So we're here at address, whatever, 4E8, so that's the important part of it. So we're at 4E8, which is this instruction right here. So this is the move instruction. This is the first instruction in main. So this is going to move the literal 100 into RDI, which is going to set RDI to 100, and then we're going to change the program counter to be the next instruction. So the next instruction that executes is that call queue. So that's the 4EF instruction. Okay, so now we'll go back to the beginning of this. Remember, the instruction cycle is fetch, decode, execute, right? So we fetched that first instruction, we figured out what it meant, and then we executed it. Now we're going to do the same thing for this call instruction. So this is a much more complicated instruction. So calls do 3 main things. Well, I guess sort of 2 main things. So it pushes the return address onto the stack, which involves adjusting the stack pointer, and then it transfers control to the location that we're calling. So the first thing that it's going to do is push the return address onto the stack, which means that it needs to create room on the stack for that new value. So that is going to decrement the stack pointer by enough bytes so that we can fit another address on the stack. This is an x86-64 machine, so the address is going to be 64 bytes long, so that's 8 bytes. So the first thing we're going to do is subtract 8 bytes from the stack pointer. That means that the stack pointer is now pointing at this memory location right here, and that is where we're going to store the return address. And remember, the return address is just the next instruction after the call. So we want to come back to this move queue instruction, which is at address 4F4. So that is the address that's going to be stored into memory. So again, that was just pushing the return address onto the stack. And now we need to transfer control. So now we're going to change RIP to the address that the call instruction is supposed to call. So now the program counter is going to be 4dB. Okay, so that means that we've called top. So that means that we are here. We're going to execute the first instruction inside of top. So that's a subtract. It's going to subtract 5 from RDI. So that's going to subtract 5 from the value that's there. So that makes it 95. This is notably in decimal here, not in hexadecimal. That was just sort of an arbitrary choice. We could be tracking this in hexadecimal. That's fine too. All right, and then the next instruction that we want to run is 4df, so that's just the next instruction after the sub. That is another call instruction, so we're going to repeat the procedure of pushing the return address onto the stack. So the return address in this case is 4E4. So again, the first thing we're going to do is subtract 8 from RSP. Note that we're working in hex here. So this is going to go from 80 at the end down to 78. And again, if that value surprises you, then you should review how to do subtraction in hexadecimal. So this is going to be the next slot here, and we're going to write the return address into that location on the stack. So that's the place that we're going to come back to, which is the instruction after the call that we're currently executing. All right, so now that we've stored the return address, we'll go ahead and transfer control to the address encoded in the call instruction. So that's the 4D6. And now we are inside of the leaf function. So in the leaf instruction, we are going to do a load effective address, which again, remember, doesn't actually access any memory. It just does an effective address calculation. And here it's just really a fancy way of adding 15 to RDI. So we take the value of RDI, we add 15 to it, and we store the result back in RDI. So that's just going to increment RDI by 15. So now it's 110. All right, once we finish executing that instruction, we're going to just move on to the next one. And now we've gotten to a return instruction. So the return is going to kind of do the opposite of a call. It's going to pop an address off the stack, which is going to involve manipulating the stack pointer. And then it's going to transfer control to the address that it popped off the stack. So right now the stack pointer is 478. That's pointing at this address here. So that's the value that's going to be popped into the program counter or the instruction pointer. So that's the place that we want to go back to. And then we're going to remove that value from the stack, remove it in air quotes here, by adjusting the stack pointer. So now the stack pointer is pointing at this address on the stack. Note that this doesn't actually remove the value from memory or overwrite it. That's just the way the stack works in x86-64. The value is still there until it is overwritten, even though it has been deallocated because it's no longer on the stack. Okay, so now we've transferred control back to where that second call made the call to leaf. And so now we're executing this instruction, which is just going to double the value of RDI. So we're going to add RDI into RDI. So that doubles that value to 220. And then we move to the next instruction, which is another return. And that's going to do the exact same thing. So it's going to pop the next return address off the stack. Since the stack pointer is pointing here, that's the value that we're going to get up in the program counter. We're then going to increment the stack pointer again so that now we've removed that value that we just popped. And now we'll transfer control over to that return address. Okay, so now we're at this last instruction before the last return. So this is going to copy RDI into RAX. So that, in fact, is our final value of RAX. And then when we move to this return instruction, we're now going to pop a return address from main off the stack. And we don't actually know what that address is here. So at this point, our work is done. Presumably, this is the address of some place in the program loading code, which will handle cleaning up the program. But we don't have to be concerned about that because we know the value that is going to be returned. So we don't know where the execution is going to go after this, but we do know what the stack value is going to be. And most importantly, we know what the return value of this program is because main has returned 220.